All right, everyone, so this is take 2. It is Wednesday afternoon. As you can tell by the clock behind me, it's 2:59 p.m. School just ended, and I am shooting this video for a second time because, as I told many of you in class, the first one I recorded, for some reason, didn't upload to Canvas, so now I'm trying it again. So a force is a push or a pull. If I take one of my bowling pins and I push it, it will go away from me. If I pull it, it will go towards me. So I am applying a force of either pushing it or pulling it. All right, that's the basics of force. The force that I'm applying to this is called a contact force. I have to touch the bowling pin to make it go away. I have to touch the bowling pin to make it come towards me. As much as I wanted to when I was a child, I can't use some mythical force to make the bowling pin come towards me or to push the bowling pin away from me. So Star Wars, they call it force, but you have to actually touch the bowling pin to impart a force. It's called a contact force. Another contact force is friction. So if you do this, that's what keeps the bowling pin from falling off the table. If you think of, if I had this table made of ice, which is a very low friction substance, and I put this on here, then the bowling pin might slide across the table until it went off the edge. But the friction with the table is what's keeping this bowling pin in place. All right, now, when I'm using forces, I have a bowling ball, I have bowling pins. I'm pretty sure you guys know what's coming next. I am going to push this, and this ball is going to get a force from me. I'm going to push it. As soon as I let go, it's just going to be rolling with my force. There will be friction on the table, but the ball is very smooth and the table is very smooth, so the friction will be very low. And there will also be air resistance as the air bumps into the ball, but the ball won't be moving that fast, so it'll be like when you're moving slowly, you can just barely feel the breeze on your face. So friction and air resistance won't come into play because I'm only going about 2.5 feet. All right, I had to stop that to make sure it didn't fall off the table. All right, so there's my bowling pins. This ball has an easy time knocking the bowling pins down when I push it with a very gentle force like that, because the ball has a heavy mass. In Newton's laws, Isaac Newton, his second law is the force on any object is equal to the mass of the object times the acceleration. Me pushing the ball is giving it an acceleration. The ball itself has mass. When I push it very gently, it already has enough force due to its mass and the speed that I'm pushing at to knock over the bowling pins. If I use this ball instead, it has a lot less mass. It's a lot lighter. When you push it, it doesn't even hit the bowling pins, but let's do it here. When you push it, take 3, and we'll see if we can get this to work. It didn't do anything. It made it rock back and forth, and now my ball is loose. All right? It takes a lot more acceleration, a lot more push to make something this size knock over a bowling pin. Okay? So you have to throw it with a lot more force. The bowling ball, because M is higher, you don't have to throw it with as much force. So in this formula, if you know that you need a certain size force to knock over the bowling pin, you either have to increase M or you have to increase A. Or you can increase both and just destroy the bowling pin. All right? So what we've been talking about are contact forces, friction, drag, which is when you, again, when you walk through the air and you feel the air pushing on you. Another word for drag is air resistance. Touch, is another contact force. Again, I have to touch the bowling pin to push it or pull it or knock it over, all right? So friction is two solids touching each other and coming in contact with each other. Drag is when a solid comes in contact with the air, so the faster you go on your bike, the more the air pushes back on you. And then touch is a non-contact force, or is a contact forces. Those are the contact forces. The non-contact forces, the easiest ones to talk about, are magnetism and gravity. And that's why I have this. So I have a paper clip on a string. It's just a regular string. There's nothing special about it. The string is pulling on the paper clip. Gravity is also pulling on the paper clip. At the top here, I have a magnet, and I have a paper clip that's made of metal. And right now, my paper clip is suspended in the air. And what's going on there is this. So there are three forces acting on this paper clip right now. There's the magnetic force, which I've drawn with an arrow. This arrow is called a vector. It shows how strong the force is, and it also shows the direction that the force is pointing. There's gravity, which I've shown with a G. That's pulling down on the paper clip. And then there's the force of the string pulling away from the magnet. So those three forces are working together. When you have more than one force acting upon something, if the object is not moving, like this paper clip is not moving, if you don't feel motion, that's called a balanced force. For example, and I'm going to leave this here so that you can see it on camera. Where's my, there it is. If I am sitting in this chair, gravity is pulling down on me. The chair is pushing up on me with what's called a normal force. I've drawn them here. So that image is me sitting in the chair. Gravity is pulling down, negative 9.8 meters per second. The normal force of the chair is pushing up with an equal and opposite force. If you added these two together, 9.8 minus 9.8 is 0. The net force acting on me is 0. And when the net force acting on me is 0, I am in a balanced state and I don't feel motion. An unbalanced state. If you are in the car with your dad, the last time I did this video, I talked about mom, and I don't want to pick on moms anymore. I want to pick on dad. Your car is at a stoplight. The light turns green. Your dad hits the gas and zooms away. You get pushed back into your seat. You feel like you are moving. And that whenever you feel like you're moving, when you feel like you're being pushed or pulled, that's an unbalanced force. That means you are accelerating. Unbalanced forces always mean acceleration. Acceleration comes in three forms, three flavors. You can go fast in one direction and speed up. That's acceleration number one, speeding up. So dad hits the gas, you go backwards as the car goes forward. Your body always moves in the direction opposite the direction of the force, because your body wants to resist changes in motion. That's Newton's second law. All right? Your dad gets about a quarter mile down the road, there's another light, it starts to turn red. Your dad hits the brake and you go forward. Because remember, now the force is backwards. Your dad is slowing down the car. You go forward. Again, you feel like you're being pushed or pulled. You are unbalanced. You are decelerating, or you are experiencing a negative acceleration. It's still acceleration. So speeding up and slowing down are two unbalanced situations where you are accelerating. Balanced situations, you aren't accelerating. That doesn't mean you're not moving, though. It just means you're not accelerating. I said there were three forms of acceleration. The third form of acceleration is turning a corner. So when you're in a car and you speed up, you go back. If you slow down quickly, you go forward. If your mom turns to the left, you get thrown to the right side of the car. Again, the opposite direction of the force. If your mom goes to the right, you get thrown to the left. So anytime you're pulled forward or backwards or left or right, you are in an unbalanced situation. Same thing happens on an elevator. The elevator is up-down. You push the button and you go up, and it feels like you're being pushed into the floor, downward, in the opposite direction that you're moving. That's unbalanced. When you're at the top floor and you get in and you push the button to go down, you feel like you're floating a little bit. That is unbalanced in the direction opposite from where you're moving. So you're moving down, your body wants to resist that. That's inertia. That's Newton's second law, or first law. Second law is force equals mass acceleration. But when you feel that unbalance, you feel that push or that pull. So I've been showing these, and I haven't really talked about the red yet. The red is a vector. A vector is a line that shows this magnitude or the strength as well as the direction. So if I bring back me sitting in the chair, gravity is pulling down, so the arrow points down. The line is 10 centimeters long because each centimeter represents 1 Newton of force. So gravity is pulling down with a force of negative 9.8 Newtons. Gravity is pulling up, I'm sorry, not gravity. The chair is pushing up with that same force, which means that this person here, this person here is experiencing a balanced force. Now, if this chair was inside of an airplane and the airplane was up in the air going 500 miles an hour, you might still feel like you're not moving. Because if all 4 of these forces are balanced, then you don't feel motion. So when the airplane gets up to its highest cruising altitude, the wings are providing the same amount of lift that gravity's pulling down, so the airplane flies along. It doesn't go down, it doesn't go up. The engine is pushing forward with the same force that air pushing on the outside of the plane is pushing back. So the plane's not going backwards or forwards, you're not going backwards or forwards, and the plane is not turning left or right. As long as all forces are aligned and everything's balanced, you can get out of your chair on the airplane and you can walk around. You can go to the bathroom, you can go ask the flight attendant for a snack, you can move around the airplane because all of the forces are balanced. The second, though, that the pilot hits turbulence and the plane goes down a little bit, you feel a push or pull in the direction opposite from where the plane went. So if the plane goes down, you lift up out of your seat a little bit. If the plane hits warm air, it goes up a little bit, you get pushed down in your seat a little bit. If the pilot has to turn left or right quickly, you go left or right, depending upon the direction that he's turning. Unbalanced forces, you feel the motion. Balanced forces, you don't feel motion, but it doesn't mean you're not moving, because when you're in that airplane, you're flying at 550 miles an hour, but in your chair, you don't feel the motion because it's a balanced situation. All right? So I talked about contact forces. I talked about non-contact forces, like gravity does not have to touch the paperclip to pull on it. The magnet does not have to touch the paperclip to pull on it. there is a gap big enough for my finger to go through, almost, in between the paper clip and the magnet. All right? I talked about multiple forces, balanced forces with a net force of 0. Net force is all the forces combined together. So again, in this case, it's the two forces acting on the person in the chair. The normal force of the chair pushing up and gravity pulling down. In the case of the magnet, it's the magnet, the string, and gravity, all pulling on the paperclip, all balanced so the paperclip doesn't move. In the case of the airplane, it's the multiple forces acting on the airplane, the engines, the rudder, gravity, the lift of the plane, the drag on the front of the airplane as the air hits it. All of those are acting on the airplane. All right, I talked about force being mass times acceleration. I talked about all of the contact and non-contact forces. I talked about the basics of forces, and I talked about vectors. So the next time you guys watch Despicable Me, which there is a clip at the bottom of this assignment, the next time you watch Despicable Me and you hear Vector talk about, I am Vector, it's a mathematical quantity represented by an arrow that shows magnitude and direction. When he says that, he's talking about the physics concept. If you have a bunch of arrows that show the direction that the force is pulling, as well as the length of the arrow. So if the forces were stronger, I would make those arrows longer. If the forces were weaker, I would make those arrows shorter. So the length of the line is how strong the force is. And how strong the force is called the magnitude. The arrow shows the direction that the force is going. So when you draw a vector, you need to make sure it has the arrow, and that it also shows in length how strong that force is. All right? So that is your basic introduction to forces. Non-contact, contact, balanced, unbalanced, and vectors. Thank you, guys.